This is what we wrote last time. Anytime work is done, it does not disappear, but reappears as stored work. What we mean by the work energy theorem. There's a change in energy in the system. So if I have a spring block system and I put an external force like my hand and I compress the spring, my hand does work. Now, because my hand is external to the system, then that means that the work of my hand has to increase the energy of the spring. However, we're not interested in the hand. Excuse me, so if I do a bar diagram for the work energy theorem, I see that my hand changes the energy of the system. So that's the important thing. There's an increase in energy. But now I'm most interested in the spring. So when I look at the spring, if I take the perspective of the spring does work, but it does negative work. And that's because of Newton's third law. Because the force of the hand is equal to negative of the force of the spring, then according to the work energy theorem, the work of the hand has to equal negative of the work of the spring. But that increased the energy of the mass spring system. One of the things that we said last time is that it couldn't be kinetic energy. Why? Because the block starts at rest and it ends at rest. So the change in kinetic energy is zero. So there must be a new type of energy, and this is what we call potential energy. And so when we look at potential energy, we can write a couple of things. The first thing that we can write is, if I just make some remarks, the first thing that I would say here is that this new type of energy depends on changes in position. In other words, we changed the distance of the spring in this system. And it's this thing. So this implies here that this new type of energy, this new change in energy, is a form of potential energy, but in our case, it's the change in the spring potential energy. Where is this energy stored? We look at the spring. The work is stored in the compression slash how do I say it? The stretching of the spring rungs. So if I have a spring, and if I look at this guy right here, so if I set this to be some distance here, and now I compress the spring. Let's say I compress it this much. So what the rungs do is that they get tighter. And so where the work goes, you could see that the work let me be careful. The stored work is in the rungs here. And then if I take that spring even more so, and I compress it even more so, then what you're seeing here, that the rungs are even tighter now. And we could say that the amount of work to go from here is, let's say, is this amount, but the amount of work to go here is even more so. So then we say that this spring has more stored work, and therefore it has a higher spring change in the spring potential. This one here has less stored work, and therefore it has a lower spring potential value. That's what we mean by the springs here. And then just one last thing here is that from the work energy theorem, if we only focus on the spring, then the negative work of the spring, that shows that we have a change in spring potential, which I typically write US. So this is what the work energy theorem tells us about the spring. So we should get into the mathematical details to actually deal with this. So now we need the mathematical details of the work done by the spring. So we need to break this up into two pieces. Last time we talked about Hooke's law. And Hooke's law, we showed here that it was a variable force. And we'll look at that. And then the second thing that we have to do here is that we need to calculate the work done by the spring. And anytime you deal with work, it turns out that this involves calculating areas. And this is very, very similar to what we saw with momentum. Momentum and energy are very similar. They follow the same type of thinking. So the first thing that we want to do here is that let's just briefly go over Hooke's law. And Hooke's law describes how a spring force behaves. And we said here that the spring force is equal to, there's a negative sign here. That negative sign is important. And then we get something called the spring constant, and then we have the displacement here. So this right here is Hooke's law. And what you're going to find here is that the negative sign is probably not an important thing that I can think of that we really need right now. But if I was to look at this here, I would then start to say, Okay, the first thing I would say is that the negative sign implies the spring force is a restoring type of force. And what this means here, or what this implies here, is that when an object moves away from the equilibrium, the spring force forces the object back towards the equilibrium. So I'll show you that in a minute with the picture. The second thing here is that we talked about the spring constant. Last time we said that the spring constant, K, this tells us about the strength required to compress / stretch a spring. Now, we got to be really careful when we talk about springs like this. This right here is what I would call a physics / ideal spring. And they really don't exist in nature. Real springs only behave in one direction, not two directions. And so in this course, we'll be dealing with only physics springs. And so here's what we find. If we have a strong spring, like car springs, these guys are hard to compress or stretch, and therefore they have a large K value. If you have a weak spring, like the ones that we did in the lab springs that we've used this semester, then these guys are easy to compress, and therefore they have a small K value. So then the other thing that it depends on the compression stretching distance. And this is what we call delta X. And to remind you that the spring force is a variable force. So what we said earlier here is that the spring force is a variable force. It's the only variable force that we will encounter in this course. So to show you what I mean by that, you already have experience with this. What we said last time here is that imagine that I have a spring attached to a mass like this. So if I hang this spring here, there's a point here, which we call the equilibrium point. So when we call this the equilibrium point, that means here that the net force is equal to 0. So if I say that the net force is equal to 0, then it means here that we have two forces. We have the force of gravity, and we have a spring force. They balance each other out. So if I consider, so this point right here is called x equal to 0. So now, in this first state, what I'm going to do, I'm going to stretch the spring. So if I stretch the spring, I'm going to stretch it till it gets to, let's say, right here. So if it gets to here, you have to imagine how hard you had to work to pull down the spring. So when you're doing this here, you're going to see that if I displace the center of mass by this distance x, you're going to find that there's going to be a spring force that's going to be larger than what it was at the equilibrium point. And that's because I've stretched it. So now, experience shows us here in the second situation that if I take this spring and I pull it down even further, that if I pull it down further, what you're seeing here is that I have to pull down much harder. And the reason why I have to pull much harder here is because the spring force has actually changed and now is larger. So in other words, if I have the same spring, which means I write the same spring constant, if I only bring it down a little bit versus bringing it down a lot, then the strength of the spring force increases, it changes. This guy can be this big versus this one being this way. In other words, this guy is a smaller force. This one is a larger force. So it depends on the distance that you pull it down.